Thank you very much. So this is Ajay Sharma. So I'm working in John Hopkins University with the Professor Geetanath Laboratory for Accessible MRI. So today's my presentation is more about research. So we as a lab are working in a low field MRI. We are doing a brain imaging of low field healthy volunteers, and we have a low field scanners in our lab that basically lab even used to build a zero point 0.2 Tesla scanner, as well as we have a 47 milli Tesla scanner in a lab. So one of the study conducted by the group of lab members, so on the Nipah virus. So today I'm going to present that study. So it is about the enhancing low field MRI using deep super resolution for Nipah virus neuroimaging. So basically, if we talk about the Nipah virus infections, they are deadly, and they first emerged in like Malaysia 1998, and then its outbreak usually in India, Kerala 2018, where 18 out of 23 people died. So however, the major fact about this infection is that mortality rate is very high, and it is in the regions such as India, Bangladesh. Its occurrences are very frequently, and most important thing is that human to human transmission is also feasible. So it is classified as a high contagion pathogen. So if you see the transmission and mortality of its, usually initially it started with the pigs, fruit bats, but now human to human transmission is also feasible. So you can see how the sources, like from the Malaysian variant it came, and in India, Bangladesh it came, and major when the infection occurs, it affects the neurological functions. So you can see the lesions in a brain of one of the MRI, human MRI. So MRI, but whenever there is a neurological changes, MRI can help monitor and differentiate the infections. It can detect lesions, brain lesion, inflation, and monitor brain changes. So using MRI, we can monitor like brain tumors, if there is any like changes in the hippocampus, amygdala, we can observe those changes. So if we talk about the MRI, we can say that 66% of the world does not have access to MRI, since the high field MRI scanners are situated in hospitals, static regions. Some person need to go to the scanning room, and if there is any critical situation in a like emergency or during the infectious disease outbreak, so it's very challenging to use those scanners, high field scanners. So accessibility is one of the major challenge. So if we see the reasons where higher the population, lower the access of the MR scanners is there. So if we talk about the worldwide access to MRI, it is severely disproportionate. So if we see high income countries, MRI accessibility is there, but whenever we move to low income countries, MRI is a little not that accessible. So almost if we see the reasons, Southeast Asian countries, uh, where there is a higher population, and remote regions, accessibility of MRI is very less. So what regarding to the NIV neuroimaging, so needs an accessible solution. So its outbreak can be higher. So whenever there is outbreak, you need to monitor the neurological changes, so that MRI can do easily. So we move towards the low field MRI scanners nowadays to improve accessibility. Like these low field scanners are portable, as you can see from the screen. Number of scanners, low field scanners built nowadays. Like we have a multi-wave 0.047 Tesla. There is a high profile scope, and other Siemens scanners, so that are available as a low field. So basically, whenever we move from 1.0 above Tesla, we usually see it 1.5 Tesla. We see it like a high field midfield, and low field is usually zero point 0.1 Tesla less than, we categorize it as low field. So if we see earlier studies of low field MRI, so we can see that for stroke detection it is used, for brain tumors it is used, for hemorrhage it is used, like 64 millitesla hyperfine scanners. So in this particular study, we are conducting NIV infections using non-human primates. So what does the NIV in neuroimaging actually needs? It's infectious and it can be monitored on in a very like VSL4 facilities, where we need large kind of suits to cover prevent infections. We need like a fully disinfected surfaces, so rounded or seal hardware, so without the risk of puncturing anything. So while monitoring these things, we are conducting our study in a VSL4 facility. So our study is usually three phase. One was a retrospective analysis, was performed on the high fields NHPs, non-human primates, using a simulation-based study. Then a prospective study was conducted, and in the future, in vivo studies will be conducted. So in the retrospective study, there were three green monkeys. Using a aerosol, we incubated them with the infection. So there was a multiple time point imaging acquired after every 3 days. Mainly we are using T2 flare and T2 to monitor the infectious lesions, right? So our low field questions were mainly like spatial resolution for lesion detection and potential characterizing lesions. So initially we simulate from high field data to low field data at different resolutions. We can see that in the yellow line showing the lesion. So we identified that one by one by two is where we can see the lesion. And but the reason for conducting the retrospective study is that there is a matters to invest time in low field scanning. So we identify that at low field, like low resolution images, we can see some lesions. So uh, there are some 3D and simulated images of a flare imaging, so where we can see with the yellow line a lesion of interest. So in the prospective study, we have a 47 millitesla portable scanner. So we use this scanner to conduct imaging. So usually the limitations of a portable low field scanners are low signal to noise ratio and low long acquisition time. Uh, but this accessible NIV imaging needs such solutions. So to conduct the study, the portable scanner moved from Hopkins to Frederick NIH Center. So in the prospective study, we have a 10 green monkeys for scanned for 5 time points, vaccinated with the potential candidates. And the imaging was performed on 3T and low field. And the questions were low field questions were feasibility of imaging in a VSL4 facility and correlate finding with 3T. So in order to adopt these VSL4 facilities, one of the lab engineer designed some of the hardware RF coils to compatible with the NHPs. So following this, these are the first like representative raw low field images acquired using this low field scanner. So mainly challenges were the acquisition, like 3T and 47 millitesla. Uh, like there were high SNR in a low field imaging. We need a kind of denoising, super resolution. Like imaging resolution is less, like 2 by 2 by 5, but the high field resolutions like 1 by 1 by 1 mm cube usually better. So we also have a challenge of multiple contrasts acquired, where we need optimization of parameters, like in the during the multiple acquisitions, trying to find the optimal parameters for non-human primates. So in order to resolve these challenges, we adopted deep learning strategies. So initially we explored like unpaired image translation, cycling and a kind of model, as you all aware. So it is an unpaired training. Yes, it takes from domain A to convert image to domain B, like our low field domain to high field domain. So uh, obviously, like as you see in computer vision, there are a lot of examples of unpaired image translation using CycleGAN. It's variants like converting from one domain to another domain. So we adopted this strategy initially to high field images, where high field T2 weighted converted to T1 weighted for the optimization of parameters, and then we also adapt this to our low field studies. So the advantage for us is that we can detect the missing contrast. If there is any T2 missing, we can detect that, and there were a long T2 weighted time of scanning compared to T2 T1 weighted, so we can convert from T1 to T2 weighted. These are the advantages. Like, so in the context aware, we provided an approach like a context aware cycle GAN. So if you see the context in imaging in 3T and 47 millitesla, they have a different context of imaging acquisitions. Like context parameters can be different TR, bandwidth, field strength of one is like 0.05 Tesla, and field strength of other is 3 Tesla. This huge gap. Also, ETL, eco train length, is differs. SNR is quite different. So these can be a different context in terms of a model, the CycleGAN model. So if you see at the left, we have a low field MRI. So we have a context driven model, CycleGAN model, that we give trained a cycleman with the context, and this gives us a synthetic high field like MRI image. So the proposed framework was like, in the initially we are dependent on the CycleGAN approach with the context driven approach. So suppose we have a very low field image, we have a providing a context plus low field image to a generator of a unit for a CycleGAN, and then it the discriminator for identifying synthetic or fake images. And again, the as per the CycleGAN principle, reconstructed back to the low field image, and we can see our reference high field image. So this was the stage one of the study. So we identify there is a gap between a 3D like synthetic and a reference high field. So we again retrain the network, CycleGAN network, from high field to low field, synthetic low field train that image is trained, so to uncover the gap between um, high field and low field. So the network was trained to generate a synthetic DA-like images, so that we can train our physics informed paired models to mitigate such differences. So, and then the third stage was that synthetically generated high field image was trained against a high field image using a synthesis ResUNet model. So that gives us a final reconstructed image. Uh, but if we see the inference, so what will be the inference pipeline? So we have a stage for like low field image. Low field image is passed to a context driven generative model. This gives a synthetic image, and then synthesis ResUNet again predict the reconstructed image that is 3D like, not exactly 3D due to some variations. So if we see some of the results obtained by our models, like we have a very low field image in the first row of the, and in the second row we have a 3D like image that is generated by the model, and there is a reference high field image. So there are still large variations, but we are trying to get as closer as possible. This is another example. So where we have a very high low field image, 3D like image, and reference high field image. So in this example, we can see some test set like very low field image, results of the context driven model, and there was a little bit noise in this model. So that is then again reduced by the synthesized network. So, however, these are the actual high field images. So we are trying to generate a 3D like images, but we are still little far away. Uh, this is another example. So we also trained our model with other approaches. So in low field, so there are like SNR difference, also resolution difference, or matrix size difference. So we also tried our this model with a paired approach. Yes, we have a 3T reference and 47 millitesla, same same subject. We are training paired training against each other for 7 subjects for like total 35 data sets, and rest for the testing. So what we identify during the paid training, even after registration, how much we try to register. So these are like some slices are not able to register in a volume. So we are trying to get some kind of artifacts with this approach. So however, the SNR, PSNR, SSAM numbers are imaging like 85 or 90, but still the challenges are hallucinations happen in these images. So if we see low and high field registration challenge were clearly observed during the studies. Also, we trained another approach of physics informed reconstruction, it's taking a high field image, adding noise to a high field image, actually acquired from the low field scanners. So we added a noise to the actual high field image, making it taken a noise from a low field scanner, adding a noise until it reaches the SNR of a low field, and then recover back the high field synthetic generated image. So based on this approach, we try to reconstruct the model. Like you can see example of a high field 1 by 1 by 2 resolution and simulated 2 by 2 by 5. So finally, this is the simulated images, and we trained against high field and simulated, and try to incorporate that learning on a very low field, right? So idea of native nice modeling was taken from the previous paper from the lab, and that added a nice of a native nice of a scanner nice to a actual high field images, and then try to recover those nice. So in the physics informed DL reconstruction, so we are trying to see the predicted like T2 weighted NIV images by the trained network reduces noise, but there is a little variation that we are not able to recover. Like we have a 3T reference, 47 millitesla and DL recon, so there are still patches on it. So however, SSIM reaches to 93, but there are still a difference miles to go. So later, our two questions we have our ongoing study on this where we will detect whether there are lesions in these reconstructed compared to a real high field and low field, and also the image quality evaluation based on the radiologist confirmation. So we will ask some questions to the radiologist whether there are lesions, what is the confidence, and whenever we are trying to reconstruct image, so what's the SNR tissue contrast. So each will be measured from 1 to 5 points, and this is still an ongoing study. So if we talk about some limitations of the study, so we try to optimize acquisition parameters for very low field, so for the non-human primates, and although there were no lesions found in the prospective time points, so we have us working on a small data set like 50 data points, for 7 to 8 time points in the retrospective for 3 NHPs, and for perspective, we have 10 NHPs with 5 points each. So also on a low field, it's challenging to train radiologists to detect these infectious features. So so the main conclusions of low field and 3D findings like correlate. So simulations demonstrated the feasibility, however texture features can be more promising. So we also found that 1 by 2 mmq was there we can see lesions in the simulated images, so that determines the feasibility. So also in the future work we will focus on expanding the data sets and our models as well, and try to make sure there are no hallucinations, artifacts originated due to the high field images. So finally, I would like to thank the collaborators from the John Hopkins University and our PI, Professor Gitanath, and our lab members, Ivan, is the hardware engineer, Leo, and all other collaborators from John Hopkins and NH. So thank you very much. So this is all from my side.